So good morning, everyone. It's nice to see so many of you here. We'll have a exciting morning. So today is about how to compute derivatives and how that leads us to this thing called AutoGrad. I'm pretty sure you guys have all seen derivatives in your math classes at some time. Yeah. So here, basically, we know that this is a pretty straightforward statement. Neural networks, there are a lot of parameters in there, and they're basically a function, right? That maps input to output, and the parameters of that function, namely, are, let's just consider like a neural network of one linear layer, right? That's going to be the parameters there. It's going to be the weights W and the biases B. So we've already seen that the update rule evolved to in updating such a neural network is basically you take the weight and you take the derivative of the loss with respect to the weight, and you subtract that multiplied by a learning rate to the original weights, right? So we have no problem there. All right. So how do we calculate this derivative? So what we do is take a look at these four. Basically, we will take a look at the classical differentiation methods. Basically, how would we have done it were we classical mathematicians, and then we'll look at how we're actually going to do it, given that we're computer scientists. All right. So here, let's consider a simple function in the form of taking in two axes and involving it in these three different terms, right? So given x1 and x2, we want to calculate basically the derivative of the result to each of these, right? And so who knows how to do this? So basically just give me del y del x1. What would that be? Yes, exactly. So it's going to be 1 over x1 plus x2, and the reason is that you need to differentiate all these three terms separately, right? And similarly, dy dx2 is going to be x1 minus cosine of x2, and that's because you care about the latter two terms as opposed to the former two terms. All right. So given the same question, so basically what we've done here is it's called symbolic differentiation. So basically, we take a look at the formula or the equation symbolically, treating x1 and x2 as as numbers, but as symbols, right? So then we will think about the optimal strategy to differentiate this given equation. And differentiation is not a very straightforward process. Sometimes you would have to use advanced techniques in order to differentiate things like the square root of the sign of a certain variable, right? So then you would need to use substitution tricks to do that. So it's not as straightforward as it always be. So basically, symbolic differentiation involves choosing the right technique out of all possible techniques and then trying to apply that to any given symbolic sequence, right? So this is how we do symbolic differentiation. And given the same task, we can also approach it from the point of view of numerical differentiation. And what that means is we don't care how this expression is structured. It can be in any form. It can be even like nested functions all over the place. It will not cause any additional trouble to us. But then what we do is simply use the original formula for limit. So basically, remember that the limit of a certain function is, or the original definition of the derivative is the effect on the result variable caused by a slight perturbation of the input variable, right? So that is what the derivative actually is, and we just take that concept and apply it in the context of taking the limit of this expression. So if we select a small h, this is going to give us just the numerical derivative that we want at that particular point. It's not going to give us a formula that's going to give us every possible differentiation result, but then this is going to give us the numerical differentiation result at that particular x1 and x2 point with regard to x1 here, right? Is everyone with me? Cool. So here, so we have talked about two differentiation approaches, and it's my job today to tell you that they are both not good. So why do we not use the first differentiation technique? Why don't we use symbolic differentiation? Any thoughts at all?
It's just really costly.
It's just really costly, exactly. So basically, if we have a neural network that involves a billion parameters, then this is basically solving a billion equations. And so basically, because each parameter is going to be related to one another because they process the same input to output, right? So there's no way that these would be separate completely when you think about the sort of perturbation chain that goes from the input to the output. So all the parameters in the network are going to be joined together at some point during in the equation group, and that's going to be a messy mess. So yeah, and when we have more parameters, that's almost never doable. So you know, if you have taken the intro to machine learning, then like you know, in some versions of the course, they actually say that you know it's well known. Neural networks actually does not have to be solved using gradient descent. They do have a symbolic solution as to, you know, at least easier versions of the neural net. Like there is a way that you can solve a bunch of equations to solve for the optimal parameters for a neural net, right? But the reason that we don't do that, and instead we struggle with so many epochs and so much hyperparameter tuning, is just because calculating the actual like best solution for neural net is not always feasible, and it's probably almost not feasible. So this is why we don't use symbolic differentiation for neural nets. This is how costly it is, and a flop just means a floating point operation. So this is, yeah, you don't want to do this. All right. So, and when I learned this for the first time, I thought, hey, we just use numerical differentiation. And we can do that for any particular input point. It's not going to be as costly. So, I mean, it does not involve as many symbolic equations. So why don't we use numerical differentiation? Any thoughts? It's going to be error prone. Exactly. So there's going to be what's actually called numerical instability and inaccuracy. So basically, you don't know on what order of magnitude your input and your parameters is going to be, right? And in the world of computers, if you add 0.1, which you think might be a small number, to 0.00001, which might be actually the value of the input or the parameter, then that will actually mess it up. Like sometimes the smaller component of the number can just got ditched, and you will end up just with the h and not with the actual your actual variable that you're trying to perturb, right? So that's one case. And the other case is that if your x is like a billion, and then you add to it like 0.1 as an h, then you will just lose the 0.1. You will just have the x, so the result is the h will just become 0. So then it will not be effective in that regard. So this is called numerical instability, in which case the varying orders of magnitude of the input and the parameters will cause you to be unable to select an appropriate context variable for adding to them or multiplying with them. All right. So yeah, and this is the whole story of these two differentiation methods, and why we don't use them. All right. That's it. No, that was my part. I have the first part, right?
I'll teach it.
Cool. Do you want to? Wait, nobody is prepared to do this? You're not, oh, wait, so nobody is prepared? Are you prepared?
Oh, no, can I pick it?
I'm not sure, I haven't seen it.
You just walk through.
Can we just walk?
All right, I can walk you guys through. If that's all right with you, I mean, I can try that. So how do we split this then? How do we split this?
Split this?
It's like,
I'm taking the lesson. The connection of the implementation details.
so, okay, wait, guys. So before, when we planned this, I was to take the first point, the first part, right?
No, I was supposed to take the first.
No, check your chat history. I was the first part, check our meeting notes. But it's no problem. All right, so how do we split this now, given that we're not prepared?
Can you go?
All right, then, Darren, we just split it among ourselves.
Okay,
All
I'm
right.
gonna take the last two.
All right, I'll just do the 2 then. You do 3, 4. All right, cool. All right, guys. Here's an improvised version of this lab. I'm sure it'll be fun. All right, so let's look at what's called automatic differentiation. And the main motivation or the main technique where you by which you achieve automatic diff is this thing called chain rule. So basically, if you have a function y that chains two functions together, basically it is defined as h of g of x, right? So how do you compute dy dx? Actually, I shouldn't have showed the answer right here.
So it's the multiplication of it's HG, J, and then HG.
Exactly, right. So, so this is a very straightforward process, right? If you have two functions leading up to the entire process, then your differentiation result is just going to be the multiplication of these two components and their own respective differentiations. So, if you have this sort of a function, so basically, if x goes through two separate functions, and then these results go to h to give you y. So then how would you compute dy dx expressed by the other functions? Exactly, right? So the lesson here is that, yeah, by the way, this is the correct answer. So the lesson here is that no matter what the structure of function decomposition is in the final function, there is a way for you to decompose it into smaller functions. And if that's the case, then you can always get the final derivative that you want through the first two derivatives, or through the different components of the final function and how that differentiates, right? So it seems like this is no longer a symbolic differentiation issue where you have to think about the correct strategy to differentiate specific expressions. This is where you have to have a strategy just to decompose the function. And if each component is differentiable, then the whole thing is differentiable easily, depending on the structure, right? So, why is it not moving? If you have this sort of a function where h involves two other functions, but then each function involves a large number of parameters, right? How would you compute each of these derivatives? So basically, you wanna differentiate y with regards to each possible input variable, right? So how is that doable?
Right then, it's again you go y to g1, g2, g1, x1 to xn.
Yeah, so this is exactly right answer. This is not too different from the case we just seen, right? So basically, if we have f of x1, if we have h of x1, no, if we have f of x1 be defined as h of g1 of x1 and g2 of x1, we just decompose the h1 flow through the two functions g1 and g2, right? And if x1 was instead, the correct way to think about this kind of structure is that if x1 had been, in the last case, had been a vector, which consists of n numbers, this is essentially the same case, right? We just name them x1 through xn, but then this is the same as there only being one input parameter, and that parameter had been a vector. All right, so chain rule tells us to always decompose complex derivatives into what's called simpler parts. All right, so if we have this sort of example, right, let's take that theoretical template into a concrete example. So basically, if y is defined as the sum of these three different parts, right? So how are we taking the derivative of y with respect to x1 and x2? So it turns out that how we do it is decompose them into simpler and simpler functions, right? So we basically have to define these three components first as their own separate parts of the whole function in the first layer, right? Because they are, so basically the logarithmic of x1 and the product of x1 and x2 and the negative of the sine of x2. So these three are the primary components of y, right? So this is always the correct way to think about this sort of question. What are the first layer components of the target function, and then how to decompose even further even those first layer functions. So basically, once we have ln of x1 and negative sine of x2, those are negative, those are mostly in place already. But then the one thing that keeps us from differentiating further is x1 times x2, right? So then you would have to think about how to decompose them into, so then that will basically be a function of two parameters. So this is the structure in which we are to decompose the function. All right. So let's do an exercise, right? So we have all these components, and let's say we're interested in taking the derivative of y with regards to x1 or x2. Like, which one do you guys want to do? x1, all right. So let's take the derivative of y to x1. So what would that be expressed as in the context of all these different v's over here? So the first step will be to think about, so you know, we have defined y as v6 minus v5, right? So by expressing with y and either and v6 and v5, what is the derivative of y with regards to x1?
So it's dy, or yeah, dv, dy dv6 times dv6 dv, Jesus Christ. Okay,
No, so the first step, right? We need to think about this step by step.
just, yeah, so take the derivative of v7 and you'll get v6. Because, well, v6 is the one that contains v1. So it's like the ones that contain v1 are v6, v4, and v3.
Right. So the simpler answer that I was looking for actually is that, let me look for, is there a chalk over here?
Left, up to your right.
Ah. Cool. So I also have the pleasure of writing on the tiny bit of maybe over here that perhaps you guys will be able to see. So basically, I was thinking about dy, and we know that v6 is the one that contains x1, right? So we just need dy dv6 times dv6 dx. Does that make sense? The x1, sorry. So this is the, so this gives us a whole answer. And now our task is just to evaluate what the second term is.
Oh, okay.
Right. So then, yeah, your answer is correct. It's just, in order to think more easily, you have to, you know, sort of do this step by step. So basically, okay. So now what is dv6 dx1?
So dv6 dx1 is
dv6 dv3 plus dv6 dv4 in and multiply each of them with dv3 dx1 or dv3.
So, okay, so first of all, dy dv6, what is that? So, yeah, if we work here, and we want dy dv6.
This one's one.
That's 1, okay. Right? So now we get rid of this, and what we really want is, as our friend over here said, dv6, dv3, dv3, dx1, and dv6, dv4, dv4, dx1. All right. So, do you guys have any idea what those two terms are? So, what is dv6, dv3?
One.
That's 1. What is dv3, dx1? I mean, x1 just substitute with v1. We don't need to do that one later.
1 by v1 dv1 dx.
That's 1 by v1, right? So dv3 dx1 is just dv3 dv1, so that's just 1 by v1, right? So it's 1 by x1. All right. So what is dv6 dv4? Up to 1. And dv4 dx1? That's v2. All right, so basically, yeah, we have the answer that we want. So basically, it's this plus this. All right. So those watching the video, I'm not sure if you're able to see this, but we have just demonstrated how to use chain rule decomposition to get the derivative of y with regards to x1. All right, so questions at this point? Yes?
Are the substitutions the only thing that are differentiating symbolic differentiation from automatic differentiation? It seems like at the end of the day, you're still just using like the same kind of rules.
Exactly. So if we were to, so yeah, just to repeat the question, is sort of the substitution techniques the same across symbolic and automatic differentiation, right?
Or is that the only thing that distinguishes them? Because like the chain rule and kind of like the whole way that you approach them seems to be the same.
Is that the only way that that distinguishes these two methods? So, you know, we are now just working on what's called automatic differentiation on the blackboard, and that's not really automatic because we still have to work step by step, right? So this doesn't really count as automatic differentiation, and you know, there's only one correct answer with regards to derivatives. So, like, if I use different techniques, there's no way I get a different answer. The answer is still the same, and the technique underlying is also the same. The chain rule is the same across symbolic and automatic. But the difference, what distinguishes these two methods, is that if we were to implement every function with its own, to come with its own derivative, then we can compose these functions to form a big function as complex as a neural net, and then we would still be able to instantly get its derivative throughout the whole neural net function, just because each component is already implemented with this derivative being in mind. So the difference between these two things is not the underlying mathematical approach, which is the same, right? The chain rule is the same in these two approaches. The difference is from a software engineering point of view. The difference is that you don't need to work step by step like this anytime you have a function that's already defined with differentiable components. You can just differentiate each of the components, which already came pre-built with these components, and then you will have the differentiation with regards to the whole function. So that's a software engineering perspective.
So follow-up question would be, would it be like the same method of dynamic programming, where you're kind of like building up from the foundation, because you've kind of decomposed it into these small constituent parts, and you have the derivatives for each of those parts, you can kind of like use those parts in the final derivative as you build up, rather than disputing like everything the entire time.
So the question is this approach similar to how you would approach a dynamic programming problem, where you build up the solution to the problem with each, or you build up each part of the solution with the whole solution in mind, so then you would use each part more effectively? And the answer is yes, your intuition is correct. This is very similar to a DP approach. All right. So this actually shows the complete graph from x1 and x2 to y. So then you would be able to see that, okay, in order to get from y to x1, you would go through, v6, v3, v4, and v1 in that order. All right. So yeah, the computational cost of AutoDiff is also smaller. Yeah, we can skip this. All right. So with this automatic differentiation approach, what we need to do, basically, as we talked about, in order to build up the DP-like approach, is that we will need to generate this, what's called the computational graph of this whole function. And by the whole function, I mean the neural net. And so while we perform forward propagation, so basically the forward pass, we will need to store each intermediate variable. So basically all these V3, V4, and V6 over here. So then we use chain rule to compute the variables, and then basically that will prepare us to get the backward back, right? Because we need to also store the intermediate value of the V3 and V4, these intermediate variables, because if we don't have the value, then when we do the backprop and their differentiation result depends on their specific value, then we will need to compute this all over again, right? So during the forward pass, what AutoDiff requires is that we store the intermediate step result of each specific step in the neural net. All right, this is a little redundant, and then we will get to the third part.
Okay, hello everyone, and sorry again for what happened. So I will improvise too for this section. So okay, we'll see the difference between static and dynamic graphs. So as Josh explained, AutoGrad is a framework that allows us to calculate derivatives of any complex mathematical function in a computationally efficient and numerically accurate way. So there are different ways to implement the AutoGrad or AutoDiff. So there is static computational graphs and there is dynamic computational graphs. So okay. So for the difference is static computational graphs are defined once and executed multiple times. This means that the graph is defined entirely before the data is passed through it, and TensorFlow is the example of this. The dynamic computational graphs, on the other hand, are created on the fly during the execution. So each operation is run as soon as it is defined, and the graph structure can be changed dynamically based on the data. So static graphs are actually hard to debug, but it is more efficient. And the dynamic computational graphs are easier to debug. This is why they are usually used PyTorch in research and TensorFlow in deployment. And so again, static graphs, the derivatives of the graph operation are defined and optimized at compile time. And the dynamic graphs derivative are computed on the fly. I think, yeah. So yeah, so static graphs, optimization friendly, easy for parallelization, hard to debug, limited flexibility. Dynamic graphs is flexible, easier to debug, and slower. So this is a disadvantage for. So okay, this is a history of the implementation of different graphs techniques. Okay, so now we'll talk about the homework part 1 grad, AutoGrad, which is a bonus. So we'll go through the implementation details for the automatic differentiation. So in this homework, we will build an AutoGrad engine using NumPy that tracks and stores every operation in a sequence. Before I start, how many of you went through the code and the write-up of the homework?
I don't understand anything.
Why? Is it hard to follow?
Yes.
What did you understand about it?
It's just new, it's just new, yeah.
Okay. What is hard about it? So,
It's just new.
just new. Okay.
It's new and, yeah, like just going through the code and understanding
Okay.
the different classes and then trying to relate them to each other. It's just, it took a lot of time for me, and then I was like, okay, I have other work.
Oh, what about the write-up? So is it easy?
The write-up was easier, but I feel like the write-up also had less context than the actual part one write-up, in my opinion.
Okay.
It just said, it gave an overview, at least the way I read it, gave an overview, but not more specific about what each, like, I had to try and figure out what each class does by reading the code,
Okay.
rather than like looking at the write-up. And the comments were also slightly in different positions than what I would, because each class had a description in the comments before the code implementation,
Yeah,
rather than
yeah,
in the code.
yeah, correct.
So
So it is hard to follow.
yeah, for some people it might be easier, but for me, I'd read the description, then go to the code, then go back to the description, then go back to the code.
So, okay, I hope that I will make it easier for you now. I'll explain some of the components in the code, so, and please ask questions, so if you have. So, okay. So in the handout, you have 3 classes. Okay, you have 3 classes, the operation class, the gradient buffer, and the AutoGrad. So the first class, the operation class, the object of this class represent every primitive operation that is performed in the network. So for every operation that you perform on the data, say multiplication, addition, or subtraction, you will need to initialize a new operation object that specifies the type of operation being performed and the input and the output. So the idea here is if you are able to write backward propagation function that calculate gradients for each of the primitive operations that for more complex structure, you can differentiate those complex structure by linking these small primitive operations. So the primary responsibility of the operation class is storing the type of operation, the inputs, and the outputs. The second class is the gradient buffer, which is a helper class. So this is a simple wrapper class around Python dictionary with a few useful methods that allow for storing and updating the gradients, such as addSpot method, which is initialize a 0 gradient array for the corresponding input. And there's the main attribute is the memory attribute that holds the NumPy array corresponding to the gradient. So the primary responsibility for the gradient buffer class is storing and updating gradients. The third one is AutoGrad class. This is the main class for the AutoGrad engine. So it is responsible for keeping track of the sequence of operations being performed. Inside this class, we will use the operation class and the gradient buffer class. So we will use an instance of the gradient buffer class. We will use it to store mapping between the input data and their gradients, and an operation list to keep track of the operation sequence that performed during the forward pass. So, okay, so we have operation list, which is a Python list that is used to store sequence of operations that are performed on the input data. So in this implementation, we will use a simple Python list. We will not use a computational graph like we saw in TensorFlow and PyTorch. So the reason is because regardless of the actual network architecture that you construct, there is a sequential order which you will perform the operation. So it will be easier to use a list. And the list will do the job. So this class has 2 methods, add operation and backward. Add operation, which takes the input, the output, the backward operation. It will initialize a new instance of the operation class with the given argument and then add it to the operation list. In the backward function, you will go through this operation list in reverse order and perform the backpropagation. So at a high level, AutoGrad framework keeps track of the sequence of primitive operations that are performed on the input data, leading up to the loss calculation, and then it will perform backpropagation and calculate the necessary gradients for the model. So any questions? I think that's it. So yeah, extremely simple if you read the write-up. I think this is not accurate line. So. You don't have, so if you go through the write-up and the code and you found it hard to follow, just send us an email or write a post on Piazza and we will make it clear. So, okay, thank you everyone.